Okay. Okay, so today we discuss threefolds. So lecture 2. I'll speak about both vanishing and non-vanishing results for threefolds. So to begin with, let's recall what was the main definition yesterday. So there was the following thing. So we're going to birational maps from X to itself, or more generally, maps from X to Y, into a certain other abelian group, which was called Burnside group of the field K. So here X is n-dimensional variety, and I'm going from this birational automorphism group into an abelian group of, so it's a free abelian group, generated by n-1 dimensional birational types. And birational types, some kind of topological jargon, so what I mean is birational isomorphism classes of varieties of this dimension. And what it was doing divisors which are exceptional for phi minus divisors exceptional for the phi inverse. And that's a group homomorphism. And more generally, when you go from X to Y, this invariant is additive for compositions. So I want to say a few words about the image of this. So far I didn't explain any non-vanishing, but in principle, we still can investigate the image of this map. So the claim is when non-zero, the image of this map is contained in a special set of divisors. So here, okay, so I want to assume X is smooth projective. So then what I'm saying is the image is contained in, the divisors will be ruled, that's what I want to say. So P1 times the previous Burnside group. Yeah, what I'm saying is that when we do birational transformations between smooth projective varieties, exceptional divisors are ruled. Because exceptional divisors for birational maps between smooth varieties. So of course, that's not the case if I just start randomly removing divisors and looking at open embeddings. But in this setting, if I'm doing blow-ups, I only end up with varieties divisible by P1 in this birational sense. Then there are questions whether that's uniquely divisible by P1 or not, and maybe not, but this at least is where the image lies. Yep. Ruled means birational to P1 times something else, times a base. So uniruled means covered by rational curves, and ruled means literally divisible by P1 as a birational type. And for example, in characteristic 0, this follows from the weak factorization theorem that all such maps will be generated by smooth blowups and blowdowns. And as soon as you make a smooth blowup, that's clear that you literally do P1 bundle. But Kolar has a proof in his book without assuming characteristic 0. There's a clever way of proving this, even an arbitrary characteristic. So in part, so in principle, if you have a resolution of singularities, then you can just conjugate your map into a smooth projective model, and then you can use this. However, if you really literally want to look at exceptional divisors between singular varieties, then they don't have to be ruled. For example, elliptic cone is an example where exceptional divisor is elliptic curve, so not ruled. So one needs some kind of conditions here for singularities of X, maybe KLT or something like this, where this works. So in particular, today we'll look at threefolds. So this will be a threefold. This will be two-dimensional birational type in principle, but the image will lie in P1 times one-dimensional birational types, which are curves. So we'll be concerned in which curves are blown up by maps between threefolds. This will be what we'll be considering. So there's two theorems I want to explain today. So there's theorem A and theorem B. Theorem A says that if I have algebraically closed field of characteristic 0 and X is a threefold, then there's total vanishing. More specifically, today we'll prove a particular case. So today we'll prove this when X itself is rationally connected. Meaning that two general points are connected by a rational curve or chain of rational curves. And tomorrow we'll prove the general case. The general case just uses slightly different technology. It's kind of easier, but the technology is a bit different. General meaning non-rationally connected. And I'll explain why this is needed and how it helps. But particularly this applies to Cremona 3 over complex numbers, where we don't say anything. And there's theorem B, which is kind of saying the opposite for other types of fields. So this was like a big field. Now I have a small field. So K-number field or a function field. And function field for this theorem means that it's a function field on a variety over a different field F. So B over F is a variety. And F can be algebraically closed or number field or finite field. So I just list some relevant fields over which the links I work with will exist and will be non-trivial. But interesting thing to note is that I allow imperfect fields actually in this theorem, not just characteristic P, but also imperfect, and still we get this vanishing. It will be a formal thing, but we don't assume characteristic 0. Okay, then, yeah, I want to say that C of Cremona 3 of this case, so I look at P3, is not 0. That's the first thing. That's the first claim one can make. And so the elements in the image, so first, like, I can say something about elements in the image. So image will be infinitely generated and contain elements of some specific form. So I'm presenting some exceptional divisors eventually. And what I'm saying is that I'm not describing the whole image, but I'm just making a preview of what kind of elements we'll see here. And they will look like this. So P1 to make a ruled surface times a difference of two genus 1 curves. And it's important that I'm saying genus 1 curves, not elliptic curves, because they will have no rational points. There will be some little bit of arithmetic coming in here. So these are the two theorems for today. So here we'll need to prove some vanishing, and here we'll use some other methods to prove this non-vanishing. So maybe vanishing is a bit more banal. It means that if we go explicitly, if we go from x to x, and we are blowing up some curves along the way, we have to contract the same curves elsewhere. And this is how we'll prove this. For non-vanishing, it's kind of more interesting. So it says that this group is not generated by elements where this invariant is 0, such as finite order elements, regularizable, and so on. So it has applications to Cremona over these small fields. Yes, and it says that the group is not simple, yes. So there's a huge free abelian quotient of this group. This is what we're saying here. Yeah, so basically, the two parts for today is we'll prove theorem 1A for rationally connected guys, and we'll prove theorem B. So yeah, and the methods are different. So some kind of constructions and abstractions. So here we need to make some abstractions, and here we need to come up with clever links that we can use. So I'll have to introduce certain ingredient for this part called intermediate Jacobian of a threefold. And I'll explain it in some detail. It uses some Hodge theoretic input, but it's a standard thing one does in algebraic geometry. So certain abelian variety attached to my threefold. And yes, I'll need to explain this, and it will allow us to solve this problem about canceling curves that I blow up and blow down. So as a warm-up, let's recall what's a Jacobian of a curve. Of a smooth projective curve over C. So so let's see how this goes. Let's say G is the genus of my curve. And then there's some natural abelian variety of this dimension I can attach to the curve in the following way. So I need to recall how genus is defined. And there are kind of two definitions of genus. One topological, the other algebra geometric. And topologically, we can say that 2G is equal to the rank of the first integral cohomology of the curve. So if I look at topological cohomology, it's, there are G handles, and the Betty number here is 2G. That's one way to see the image, to see the genus topologically. And algebraically, we can do either of the following thing. We can say that we're looking at dimension of holomorphic forms. Yeah, I'm looking at one forms, and I'm looking at global holomorphic forms, and this is the genus also. So kind of, yeah, so if we don't do topology, we have to do a little bit of shift cohomology here and take global sections of algebraic holomorphic form. And then another way to present this is by CR duality, we say that it's H1 of C with coefficients in the structure sheaf. This is CR duality. Yeah, I'm not kind of assuming really like knowledge of this, but it's convenient formalism to make a certain definition. So I have this cohomology group, so H01 or H1 kind of 0. And they're the same by CR duality. So using these two spaces, one can define the Jacobian as a quotient. So specifically, what we do is the following. So we kind of connect these two spaces together. So the first, we can do this. Then I can map into the complex cohomology. So far, this was Z to the 2G, and this is embedded into C to the 2G. So not much has happened here. I just extended coefficients. But then we can project to H1 C with coefficients in O. So now sheaf cohomology. And this is kind of, if you look at sheaf cohomology, there's constant sheaf C, and this is the sheaf of functions, and there's natural map between them. And then Hodge theory says it's a surjective morphism. So now what I'm doing here is I want to take the quotient of this by this. So Jacobian is defined to be H1 CO modulo H1 CZ via this injective map. So this whole composition is injective, and it presents you with a lattice inside half-dimensional complex space. So this defines as a complex torus. So complex torus by definition means this. So you look at C to the G modulo maximal rank lattice. Then there's this theory of abelian varieties, which present this an algebraic object. So Jacobian of C is algebraic via the ample polarization. So polarization means kind of two things, and here they come together. So polarization means an ample divisor, but for abelian varieties, specifically the first theorem you learn is how to characterize ample divisors in terms of some linear data on this structure. And both of them are called polarization, and the input here to make this into an algebraic variety with a given ample line bundle, one looks at the unimodular pairing on the lattice that you have. You look at topological H upper one, you take the intersection or the degree pairing, and that's unimodular pairing. Yeah, that's a standard way to create an abelian variety. You first present as a complex torus, and then specify some linear algebra data, specifically this kind of pairing, to define an ample divisor here. So, and that's a very classical object. One of the key things about this, it completely determines the curve. So the famous Torelli theorem says that if you only remember the Jacobian as polarized abelian variety, so together with the ample line bundle coming from this polarization, determines the curve up to isomorphism. So sort of this way, the world of curves is linearized and embedded into the world of abelian varieties. So that's one thing we'll be using when we want to extract those curves that we blow up. Another thing we'll be using is the uniqueness of decomposition for these abelian varieties. So if A is now arbitrarily polarized abelian variety, then you can decompose it uniquely into indecomposable factors. And both things are important for us. There exists a unique decomposition of A into indecomposable abelian varieties, polarized. So indecomposable just means that you cannot decompose them further, and then uniqueness means that if someone else gave you another one, at least the factors are isomorphic as polarized abelian varieties. So these factors, indecomposable factors, are uniquely determined. And these kind of statements are very valuable in what we do, because typically there's lots of constellations which we cannot control, but here, when it's uniqueness of decompositions, we can extract the pieces from the information we have. So as polarized varieties, the factors are unique. As non-polarized, I think one gets this Poincare reducibility. the standard version is with principal polarization, but it also works with arbitrary polarization. It's a bit like if you have a representation and you make it into, if you put some kind of endogenous form on it, you can take orthogonal complements. So this polarizations plays the role of, it makes everything semi-simple by allowing you to take orthogonals in this linear algebra data. Without polarization, this fails in various interesting ways. If you have more than one polarization, sometimes you're indecomposable for one, but not for the other. So now I'll generalize this to intermediate Jacobians of threefolds. Now we look at X smooth projective threefold. And I'll use it rationally connected. I'll explain why. So kind of, we want to do a similar thing as before, but now our middle homology groups is H3 instead of H1. And we're trying to make up a factor as before, to make some kind of complex space by a lattice. And Hodge theory, which here was used in this quotient morphism, can be stated explicitly as a certain decomposition of this complex space into Schiff homology groups. So I put homology from 0 to 3 of various differential forms sheaves, so top differentials, second differentials, and so on. So previously we had just two pieces. One was H0 omega 1, and the other was H1 O, but now we have these pieces. And again, CR duality identifies these pieces up to duality. So CR duality says they have the same dimension. So why do we assume rationally connected? It's to be able to take this quotient, we ideally want one-step filtration. Here there's too much stuff, so rationally connected buys us that this is 0. Rationally connected varieties, there's no top forms. And so by by CR duality, this is also 0. So now it looks very much like a curve where I have like two pieces, and I'll end up quotienting one of them by the integral structure. Specifically, we can look at H3XC, and there's a canonical projection to this piece. And I'm looking at H3XZ, mapping there as before. So this morphism is usually injective unless there's torsion in your homology group. So that's standard to get right torsion-free quotient out the torsion, then it's injective. And we'll look at this composition. Previously, in the curve case, there was no torsion H1. This literally was a free group, but sometimes there's torsion in this homology. And then you define the Jacobian of X, so intermediate Jacobian of X. Intermediate means it sits in the middle, to be the quotient. And then it formally looks the same thing. So there's a half-dimensional complex space, quotient out by a lattice. And furthermore, it's polarized by the same reason. We can again look at the middle intersection form. It's non-degenerate and unimodular, and it's also polarized as this abelian variety. So this is can be given a structure of a polarized abelian variety. So I'll give two examples for how this works and generally helps in birational geometry, and then I explain how we use this. So my first example is some very classical geometry. I'm looking at intersection of two quadrics in P5. So smooth complete intersection of two quadrics in P5, that's a Fano threefold. Meaning that canonical minus k is ample. And there's a classical story about intermediate Jacobian for this guy. Namely, there's certain projective duality construction for this. So if you look at, there's a natural curve attached to this x. Specifically, if you look at all quadrics passing through your x, it's a pencil, and these are two quadrics from this pencil, so these are quadrics in P5 containing x. And because it's a pencil of quadrics, there are certain finitely many degenerate quadrics in this pencil. Specifically, you have 6 by 6 matrices, and you want determinant to vanish. So you're looking at determinant lambda 1, q1, plus lambda 2, q2 to be 0. That's a degree 6 equation on P1. And when everything is smooth, you get 6 points in the base of this pencil where quadrics are singular. So it won't be related to what I'll talk about next. I just want to give a nice example of a Jacobian. Because now what I want to say is that 6 points in P1, you need to think about hyperelliptic curve. So you look at 2-to-1 cover branched in these points. So branched in these points. And that's a genus standard computation. It's genus 2 curve. And then the claim is some kind of projective duality claim is that the Jacobian of x as a principally polarized abelian variety is the same as Jacobian of a curve. And this is not random, so this is the rational variety. And kind of to make it, to realize that this rational variety, you have to blow up this curve at some point. This curve is attached geometrically, but also when you make projection from the line, it's another way to see this curve. So these guys are rational varieties, and to make them to the standard rational map to P3 is projection from a line. So on the one side, you'll be blowing up a line, and actually it will be standard blow up, blow down one step. So on the other side, you'll be blowing up this curve exactly. This curve is kind of associated to this x in one of the two ways which are related. The first way is looking at the Jacobians and just trying to guess from the homology of your variety whether you are coming like this. And the other is this blow up, blow down. In a second, I give a formula for Jacobian of the blow up, which will make this more relevant. So I'm saying here I blow up a P1, and here I'm blowing up this curve, and kind of everything matches together. I have no clock. What time is it? Good. So then maybe I'll give you another example. So I kind of want to emphasize how it was used classically. Another example is we look at very simple threefold, which is not rational. Specifically, we look at Clemens-Griffiths theorem. So now instead of intersection of two quadrics, we go 1 degree down and we look at a cubic threefold. So it's formally very similar. Yeah, thank you. It's formally is very similar. It's a Fano variety, and furthermore, it's a Del Pezzo threefold. Its canonical class is twice the generator in the Picard group. However, what those guys proved is that Jacobian of x is not isomorphic to any Jacobian of a curve, or any curve. And that's an indication of non-rationality. So from here, they deduced that X is not rational. And this was one of the first examples of rationally connected irrational varieties. And this was one of the methods of proving that. So the key point in this proof, and also key point for our theorem A, is the following observation. What happens when you make a blow-up of a threefold? I have a rationally connected threefold as before, and I blow up a smooth curve. So everything's smooth on this blackboard. So the key point is what happens to the Jacobian. Namely, is the Jacobian downstairs together with the Jacobian of the curve you blow up. So this is when Jacobians of curves start meeting with Jacobians of threefolds. If you blow up those curves, you pick up the Jacobians of those curves. And this is as polarized abelian varieties, importantly. So not just a complex story, but polarization is preserved. So we'll be using this in our uniqueness of decompositions. Right, so what I'm saying is if you blow up a curve, the Jacobian goes up by this amount. And now maybe this kind of becomes relevant. If we look here, if we believe this rationality construction, blow up of a line, and then blowing up a curve C on this other side, what it tells you is, okay, Jacobian of P3 is 0. It has no middle homology. You blow up the curve. The Jacobian here is now Jacobian of this curve. But Jacobian of doesn't change under blow up of this line because it's a line. It's trivial homology in the middle. Yeah, so like this geometry is one way to prove this isomorphism using that key observation. In this case, when X is smooth, C is also smooth. When you make repeated blow-ups, it looks a bit like a disconnected curve, right? But we don't have to look at reducible curves for these arguments. So, okay, this was classical rationality examples. How will we use this? So what I'm saying is by Torelli theorem plus uniqueness of decompositions, the two theorems I stated over there imply that C is determined by this pair of varieties. So we don't care even what the map was, but if there is a map like this, then the curve is determined by your varieties. Specifically, you compare the two Jacobians before and after the blow-up, you decompose everything, you collect the remaining factor, and then recover the curve from the Jacobian. And this is like the key point for the proof of the vanishing theorem, that I'm supposed to recover what I have blown up just by looking at source and target. That's an example of the situation. Okay, so let's prove the theorem now, this vanishing theorem. So it says that X is as before, so rationally connected smooth projective threefold. I want to know how to prove that C of bir X is 0. It's kind of formally follows from here. One needs to set up the machinery, and then it works. So the machinery is as follows. So it's kind of Motivic invariants, mini-course, so I'll give you a new K0 group, so K0 of abelian varieties. So this will be the bookkeeping group for abelian varieties. So generally K0 means that I'm about to give you generators relations, and relations will be some kind of splitting into pieces. So generators are isomorphism classes of principle of polarized abelian varieties, of polarized abelian varieties as before. And relations are decompositions. If I take A1 times A2, I declare it's the same as the sum of the two generators. So as soon as you have some kind of nice category with direct sums, you can run this K0 construction. The beautiful thing here is that because of this uniqueness, that's an easy kind of group. So from uniqueness, it follows that this group, which potentially could be quite complicated due to cancellations, is just a free abelian group on indecomposable abelian varieties. Indecomposable polarized abelian varieties. So kind of the relation tells you that you only have to care about indecomposable ones, so definitely they generate, and then there's no relations by that theorem. So it looks a bit like semi-simple kind of category, where decompositions into simples of some sort is unique. So everything is polarized. So I didn't put it inside here, but what I mean is polarized. Non-polarized, you can just say that you have some polarization and impose this relation without caring about polarization. Then it's a very complicated group because there's no uniqueness, and certain things can cancel out in different ways. The beauty of this thing is that the class of variety determines the variety. If you don't put polarization in, you have a complicated group, and the class will probably determine isogeny class, but not the whole isomorphism class. Did I answer your question, sorry or not? So this is the definition. So yes, kind of you can make it more general. You can have a category with this operation, which is associative, and then you run this definition. Maybe additive category, maybe that's the word. I didn't even have to use this K0. I use it for didactic purposes, namely that it's a free abelian group. K0 is usually more complicated, but if it's more complicated, we use K0, and here we can just say exactly what it is. Okay, so I want to look at a certain composition here. So now, instead of x, I have x and y. So the proof will be simpler if I allow different varieties at this point. And then eventually, for self-maps, we get 0. So what we'll do is this. So we go from pure x to y into, now you have to remember what I was telling you earlier. So the image of the invariant is divisible by P1, and here I put Burn 1. So these are isomorphism classes of curves. And the image lands here. So now I want to go to K0 of these abelian varieties. So I have to cancel everything, but I kind of need to set up the machinery for the cancellation. So I introduce a map J, which sends P1 times a curve to the Jacobian of this curve. It sort of divides by P1 and takes a Jacobian. And I don't worry about any other classes. All my classes here will look like this. And kind of, I want to look at this composition, which is J composed with C. And the claim I'm making about this composition is that J composed with C is an easy thing. So you have to look at your source and target and look at their intermediate Jacobians. So J of the target, intermediate Jacobian of this guy minus intermediate Jacobian of this guy. So kind of, I want to use Torelli, and to make this work, I look at this composition. What is the proof of the claim? So here is convenient to separate x from y, because now I want to say I look at generating maps. So by the weak factorization, which I only briefly mentioned before and now I'm using, so if any birational map between smooth projective varieties and characteristic 0 decomposes into smooth blow-ups and blow-downs. So I'm looking at the formula I'm proving, and both sides are additive for compositions. So, okay. So both left-hand side and right-hand side are additive invariants, so additive under compositions. Therefore, I can check one generating morphism, just a blow-up. So hence, can assume, can only check, just check the map we understand very well, which is the smooth blow-up of the curve C. Okay, and then I set up everything in such a way that in this case, left-hand side just equals minus the Jacobian of the curve, and also equals to the right-hand side. Yeah, so what I'm saying is that if I look at this side, for example, by the key fact about blow-ups and Jacobians, this thing is literally the Jacobian of the curve with the opposite sign, because that's what we do. And if we look at the other side, I told you yesterday how to compute this invariant for the blow-up. In particular, we have to look at this surface, the exceptional divisor, and then we do the J, and J does the Jacobian of the curve. So both sides are the same thing. Right, so kind of in these proofs, it's important to make some kind of claim, which then you can check for a single blow-up. Then you win. And this is an example. Right, so this is important. Like what it says is that this composition depends on the source and on the target only. So for self-maps, it's just 0. So this proof is almost finished. We'll be using Torelli theorem once again. Okay, so by the claim, from this claim, it follows that J of C of bir X is 0. So, yeah, now I'll do some hand waving. One can do a bit more formally. So I'm looking at the curve I have blown up first. And this thing tells me that somewhere in this composition, I'm doing weak factorization. So I'm decomposing into blow-ups and blow-downs with smooth centers, typically curves, but also points. Points are easier. So this claim, together with Torelli, tells me that I have to contract onto an identical curve at some point. So, namely, all the j's will cancel. So it means that there will be a j of this curve somewhere in the other direction. And by Torelli, it must be the same curve. Therefore, I'm saying that this center cancels this center. And then I keep doing it with every center. OK, then there's a little problem with genus 0 curves, like points and genus 0 curves. But they you just cancel by Picard rank considerations. So the main thing is to cancel the complicated curves. And then you end up counting P1s and points, and they also all cancel by the Picard rank, like for surfaces. So this cancels all curves of genus at least 1. So Torelli theorem for genus 0 is not very interesting. Jacobian is 0. And there's one P1. However, in this factorization, there could be points and p1s. And then you get rid of blow-ups of points and blow-ups of p1s by pk rank consideration. Beautifully, if we blow up a curve, a p1 or a point, the exception divisor is the same. Namely, if you blow up a p1, you get a ruled surface. If you blow up a point, you get p2, but birational is the same surface. So from this Motivic perspective, that's the same kind of operation, and they all kind of cancel somewhere by pk rank. What's the time? So I'll now go to the second part, and we'll do something totally different. Specifically, I'll have to present you with an interesting birational maps where things don't quite cancel. So if K is a number field or a function field, and I have, so it's a slight improvement, actually, or major improvement of what I said earlier. So I'll do not only n equals 3, but all higher n at the same time. I'm looking at P3 over K. So Cremona 3 is non-zero and infinitely generated. So yeah, because there was a question earlier. So in particular, what we get is that abelianization of the Cremona will surject onto like an infinite direct sum of copies of Z. Okay, maybe it follows more from the proof than from what I just said, but the proof will produce invariants in the image going in being linearly independent, and then you have such a consequence. And in fact, because it's free, you also have a splitting, so you earn this as a direct summand in your abelianization. Here. Yeah, thank you. Yeah, thanks. Thanks. So 3 is OK, and then 3 formally will imply higher ones. Yeah. So it depends on your field. So your field is countable. It should be countably many copies, and if your field is uncountable, you should be able to get uncountably many copies, indeed. I'll tell you where this variation comes from, what are these classes parameterized by. So the proof is some kind of induction, and peculiar, we start at dimension 4. So this is the first case we cover. So start with n equals 4. Then n equals 3 requires a bit more work compared to this case. This is a natural place to start. Yes, I have to remind you of a certain link. Okay, so we consider the following diagram. I start with P4 over my field. So far field is arbitrary. What I'll need is, I need to look at arbitrary genus 1 curve, so elliptic quintic. So meaning the curve of genus 1 and degree 5, and by Riemann Roch, it sits in P4, like elliptic cubic sits in P2, and elliptic quintic sits in P4. And then I run the link by blowing up this curve. Yeah, and I put some kind of curly letters here because later we'll take hyperplane section. This will become normal letters. Yeah, so the claim is after we blow it up, we resolve a certain linear system of quadrics passing through this curve. If you look at, so okay, there's a little bit of kind of theory here, and I'm giving you the facts we'll need to use. So such curves will be complete intersections of quadrics passing through them. And you count how many quadrics you've got, and you end up mapping into P4. So I have a linear system, and that's the base locus of my linear system. Therefore, I'll resolve this map by this blow-up. So I have another arrow here, and another kind of non-trivial fact now is this is also a blow-up. So it's a blow-up of something else. It's a blow-up of certain surface, which is an elliptic scroll on the other side. So that's an example of something called simple Cremona map. Considered by Crowder and Katz, who classified them in some situations. Basically, what one needs to know is in Cremona maps which have one blow up here and one blow up here, or maybe more generally resolved by one blow up. So in small dimension and small codimension, these are classified. That's one example that people do. And this part is non-trivial. It's a blow up of some surface. Right, so I want to use this map phi, basically. And so this will be phi capital. OK, so what I want to tell you is the exceptional divisors on both sides. Exceptional divisors, and I need to kind of see if they're the same or not. They'll kind of look very similar, but they'll be a bit different. Specifically, let's see. So yeah, so this is the surface. That's important. OK, so let's see. So basically, in this situation, when I do one blow up, one blow down, exceptional divisors are ruled over the corresponding centers. So we can start with E. And because E was codimension 3 in P4, I end up with P2 bundle over my center C. Right, so this is because E is created by blowing up this curve, and this is the exceptional divisor when I blow up this curve, and that's the threefold sitting in the fourfold. That's one side of the equation. The other side, yes, thank you. Yeah, indeed, so ruled over this center. The other side is very similar, apart from we have to analyze what is S, actually. OK, so the other side, I do a codimension 2 blow up, so blowing up a surface, so I have to put this in dimension 3 by doing this. OK, and then I have to say something about this C and S. So I have to recall this link. OK, it blows up curve C inside P4. I want to tell you what it contracts. So what it contracts will tell me what is my divisor D and what is my surface S, the center of the contraction. So because of this form to H minus C, one checks, you contract secant lines. So you want to know every secant line intersects this thing trivially, therefore they're all contracted, and because there are the right number of them, that spans you the divisor that is exceptional for this map. Specifically, they'll be contracted along the ruling, along this kind of line direction, and this is this P1 direction. What I'm saying is that the surface S is birational to symmetric square of the curve C, because you have to choose 2 points, X and Y, make a unique secant line, and I'm describing the base of the contraction. The base of the contraction is choosing 2 points, unordered set of points on the curve. So this means C cross C modulo diagonal action. Right? Unordered set of points. That's the surface we see on the other side. And now the interesting thing, it starts looking very much like the elliptic curve C, but it's a bit different because you know this thing about symmetric powers of curves have to do with their Jacobians. So here the relevant thing is you look at peak 2 of C, and then you get a P1 fibration over that. So peak 2 of C is very much like peak 0 of C or peak 1 of C, except for it parameterizes degree 2 divisors on the curve. So this map sends you these 2 points in the corresponding divisor class of degree 2 on C. And I want to call this curve C prime, and I want to argue it's not the same curve. Specifically, for us to compare, C is actually peak 1 of C. Kind of elliptic curve is isomorphic to its Jacobian, and in these terms, when you have no points to subtract, it's isomorphic to the first Jacobian, right? It sends a point to a point. Here, however, we're doing second Jacobian. And in principle, they can be a bit different, and they are different. So what I'm saying is that they are not isomorphic unless C has a point. So there's a lot of negation, so let me spell it out. In the familiar cases, when I have a point, I can just subtract this point and then make an isomorphism. What I'm saying is that when there's no rational points on my curve, these are two different genus 1 curves. So that's, and people number theory study this kind of torsors, that there's like the main guy, peak 0 of C, that's an honest elliptic curve with a point. And this guy has no point, this guy has no point, and they will be not isomorphic. That's a standard number theory computation, which I won't explain. Yeah, so basically, the condition on this field, on that field, was to ensure that such curves exist. So kind of, the link always works. So kind of what I want to say here is that this is now birational to P2 times the other genus 1 curve. However, over algebraic closed field, that's the same curve, and we don't get anything, as we know from the previous theorem. And in this case, we do get twisted forms of the same curve. So, yep. Peak 2. Yeah, so if you think about peak D of C, this is a Picard variety of the Picard variety of degree D divisors. Like, usually we don't, over algebraically closed field, we don't make this distinction. You can say 0 or 1, you can just add or remove a point. Yeah, like, for example, peak 1 is Picard variety of degree 1 divisors, and this corresponds to points. And peak 2 is some other curve. Also, genus 1, it's a twisted form. If you extend scalars to k bar, it's the same curve, but over k, it's a different twist of the same curve. So using this, one can finish the proof for P4 quite easily. So you look at this map, and now we compute that C of phi is so P2 times the curve we've blown up minus the curve we have contracted on. And I want to argue it's non-zero in our situation. So, okay, I won't say it's non-zero when there's no rational points, because if, I want to kind of explain why they're not birational. So if I had a birational map, then there's a standard argument that we can contract the rational curves and get the basis of these fibrations also birational. So using something called MRC fibration, which I'll speak about tomorrow for some other purpose. MRC fibration, maximally rationally connected fibration. So the one which contracts all the rational curves you want to get rid of. You get C is birational to C prime. But this is, of course, not the case, because if they were, they're smooth projective curves, they have to be isomorphic. But it's a contradiction. Under this assumption, because they are not isomorphic here. What's the time? 2 minutes. Okay, very good. So in 2 minutes, I'll explain the higher dimensional case and the lower dimensional case. 1 minute for each. But maybe we started 1 minute late, maybe. Okay. Maybe I'll just say in words what you have to do for n equals 3. For n equals 3, you have to take hyperplane sections on both sides and reduce this length to dimension 3. Namely, you take one of this quadric passing through C on this side and P3 on the other side. So it stops being symmetric like this. You go from quadric to P3, but still with some work, you can use the same construction. And the easier case, which I maybe spell out, is what do you do for higher n? You can just take this map phi from P4 to P4 and multiply it by identity. You can take any kind of, you can like make other, if you want to go from Pn to Pn, you can take this model, which acts as phi here, as identity here. Yeah, so doing not much, just take some kind of cylinder over your construction. And then formally, the properties of our invariant is that you have to multiply the old thing by whatever you take here. And then you say it's non-zero. So why do you say it's non-zero? You just do the same argument, and here it's not a P2, but a higher Pn. But by the same argument, if you have a higher Pn here, you get a contradiction like this. So basically what I'm saying is that curves are not stably birational unless they're isomorphic. Yeah, so they cannot be stably birational unless they're isomorphic. Yeah, so that's the higher dimensional case, just formally multiplying, keep multiplying by P1. And the n equals 3 requires a little bit more explanation. And that's a good place to stop. Yeah, it's just the same, apart from this other curve here becomes isomorphic to the original curve. So they are twisted form of each other in a sense. When you pass to algebraic closure, you earn a point, and these curves become isomorphic. So the link works. However, this thing is 0. And it's 0 at this point because they are isomorphic. It's a valid thing, but there's no contribution here. So we have something with K3 surfaces for P4. For curves, we also have genus 1 curves of different degrees in higher projective spaces, which we haven't written down yet. I think higher genus curves are not supposed to act like this. So I think, yeah, furthermore, I didn't explain this, but this, the theorem A with cancellation says that for threefolds, curves of genus 2 and higher do cancel altogether by Serre-Storelli theorem. So for threefolds, what we'll have to care about are curves of genus 0 and 1, and then genus 1 curves indeed appear, and genus 0 curves typically won't appear for some other motivic reasons. So genus 1 curves are kind of the contributors to threefolds, apparently. But whether for threefolds there's any other kind of situations, I don't know. There's another link which we don't know what happens. There's some other threefold link like this which we couldn't solve. So it's a very fine line here between constructions and abstractions, namely that for threefolds the only constructions should come from genus 1 curves, and then we don't know other such constructions for genus 1 curves.
So if you take two non-isomorphic genus 1 curves, would they give the different examples in your?
Yes, thanks. I forgot to say this. Where is this infinitude is coming from? I can start varying this curve, and it's the whole moduli space of those curves. Therefore, definitely we get infinitely many of these inputs, because we get contributions of this form, and when the curves are different, the contributions are linearly independent in the target. And so indeed, varying this curve, we get infinite direct sum. And if the field is, so it will be the same cardinality as the field you work on. Yeah. Genus 1. Yes, all these contributors have genus 1, and that's kind of theoretical reason why it's genus 1 only, because this Torelli theorem will cancel all the genus 2 contributions with some more work. Yeah, it's interesting.
This the J there is injective.
So it's injective apart from P1. Yes, it's the kind of the nice way to finish the argument would be say it's injective, therefore we're done. It's injective apart from P1, which we have to, yes, but you're right, this would be, yeah, maybe if I would carry J plus difference of PK ranks, I could just say that I make something injective, yeah, thanks. Instead of saying that kind of diagram. Thank you. What happens on the question session? Who asks and answers questions? I stay here. Good. Okay. Ping pong lemma, right? Ping pong lemma. I forgot.